After seeing some very nice results from real experiments, now we go into Monte Carlo La La Land, or wishful thinking land. I'll show you some simple framework that we are developing. That's a simple and fast toy model-based radio detection simulation. So the idea and the motivation for this is that we want to investigate with just a few simulations, large areas. We want to see, investigate low detection probability events, so those events that come from directions and are really hard to see. And we want to see effects, geometrical effects due to array layout, like an asymmetric array, infills, stuff like that. And we want basically a fast aperture estimation calculation. Another main goal of this is to try to optimize the generation of simulation libraries that you want to do when you're going to study your detector in more detail. So you need actual full simulations of everything. So the idea here is to sweep the phase space, basically looking at the trigger probability, depending on the characteristics of the shower, and to estimate the total and the relative number of full simulations that you would need to do this kind of more detailed study. This is especially important for neutrino and tau decay events, because you have extra variables with those. So a regular shower, we always start basically at the top of the atmosphere, while neutrino showers, we'll have this extra variable, which is the depth where the first interaction occurs. So RDSim is really fast, so it can do everything that I showed you we wanted to do. So we can simulate like millions of events in a very short time, so we can handle large areas, these geometrical studies, low probability triggering, etc. And we can also investigate all the geometric effects, so we can put like thousands and thousands and thousands of events and see what comes out. The simulation takes into account main characteristics of the detector, although in a simple way, so we can have different trigger setups, different thresholds, we can include antenna patterns, and even a simple particle trigger simulation based on muon density maps, but I won't have time to go into that. RDSim can handle any Zaides downgoing shower that includes like charge current neutrino interactions, neutral current as well. So we inject into IDES or Zaides the products that were obtained from Herwig. We also do tau lepton decay initiated showers. For that, we use tau OLA to get the products of the decay. And we can also propagate taus from the creation to their decay. We use fast toy models for this. The main one is this radio emission toy model that I'll talk a little bit more about. We have a very simple toy Monte Carlo that actually runs outside of RDSim to get some parameterizations for tau propagation. And, oh, sorry, wrong direction. So about the emission toy model, radio emission toy model, it's based on theoretical polarizations and assumes an elliptical symmetry. It's able to disentangle the Ascarian and geomagnetic components of the radio emission to estimate the electric field or the peak of the electric field along with its polarization anywhere on the ground. The input are full simulations, full Zaire simulations with specific arrival directions and just a few antennas. This is actually an extension of an old toy model that we developed long ago in Santiago. So now this toy model can be rotated so that we can use one simulation of a shower coming from one direction and basically torture it to make it think it comes from another direction. And so we also included like early, late effects that are really important for more inclined showers and a simple scaling with energy. So now we can sweep the phase space with much fewer simulations. So basically, that's what we do. We have simulations with antennas along this line, and we decouple the Ascarian geomagnetic components. So we have like the amplitude as a function of distance to the core of the Ascarian and the geomagnetic components. We have the expected theoretical polarization. So if you want the field in an antenna here, we just assume that each of these emission mechanisms has a elliptical symmetry here. We find out where we should sample the Ascarian and geomagnetic and just add up the polarizations and add it vectorially here and get the field there. So this is just a test of the rotation of the toy model. This is a dedicated one coming from the west, and this is actually a rotated one. There is very little difference, around 2% in this example, so this looks good. We also compared the results of the toy model with full simulation. So this is fully simulated antennas and the same antennas using the toy model. You can see here along this line of antennas here in this direction. You can see in stars is the old toy model that is pretty far away from the red dots, which is the full simulation. And the blue is the new toy model that has these early late effects. So it can better describe this kind of more inclined showers. As an example, I took overall LWA and simulated a few events in this array. Overall LWA stands for Owens Valley Radio Observatory long wavelength array. It's an array in California in this Owens Valley Observatory. One of the main characteristics is that with the upgrade that we are doing, we are going to be able to search for cosmic rays alongside all the other scientific goals of the detector. We are in the middle of an upgrade with more antennas, new electronics. It was supposed to be done already, but you know, COVID, so it's still ongoing. Another important characteristic here is that our trigger is radio only. So we have some RFI rejection at the FPGA level. That's based on, I'll show in another plot. And so if the FPGA triggers, it triggers the whole array and sends the traces to a computer that does further rejection based on does it look like a cosmic ray? Do we have airplanes, airplane tracks? Does it come from a direction that we know there's lots of RFI, etc.? So this is how overall looks. You have a very dense core of antennas at the center, and you have these outlier antennas. The array is separated in subarrays that are inside, connected to the same FPGA. And here, what it does to get our trigger rate to a sane level is do a rejection that's based on veto antennas that are further away. So if you have, for example, this trigger in this region, the orange region here, and you have also triggers in these outlier antennas that are further from this region, then it flags it as RFI and discards it on the spot. So these are some simulations at overall from vertical showers until 60 degrees. So you can see that for more vertical showers, the footprint, of course, is smaller. So you need to be close to the core to have a nice event. And as I get more and more inclined showers, the footprint increases, and yeah, up to 60 degrees, where you basically light up half of the array. And as I said, this kind of fast simulation can be used to look at kind of a border and the effect of infill. So this is basically what I have here are triggered events. The dot position is the core position, and the color is the number of antennas that triggered for that event. So we can see here that at low zenith angles, basically I have holes in my array because there are too few antennas. And the effect of enriching the event close to the core is just around the core. But as I go more and more inclined, the footprint gets bigger and bigger, and you have more and more triggers further away from the center, and the effects gets bigger, and at 60 degrees, for example, the effect of increased number of antennas due to the core is basically the size, the area that's affected is basically the size of the array. And I can have antennas that, showers that land very, very far away from the array and can still trigger an event. So this is one of the reasons we developed this. Is just a fast aperture estimator. And this is what we expect for OVRO. This is not a full simulation because I did not implement that veto trigger yet. So this is without taking that into account, but shouldn't be much of an effect, especially at lower zenith angles. And this at 10 to the 18th, so if you do a back of the envelope calculation, you expect something like 50 10 to the 18th or thereabouts showers per year. So now going to downgoing neutrino events. So we have a neutrino that comes, it interacts somewhere in the atmosphere, creates a shower that can be detected. So in order to simulate this, we divide the atmosphere in slices of the same thickness in grammage. So you have the same grammage in each one. That means that's a good approximation, is that you can have an interaction is equally probable in any of these slices. So that's how we take that into account. You have more slices closer to the ground. And of course, you have a bigger probability of interaction of the neutrino closer to the ground. We have internally this variable here, which is the height above ground where the interaction occur, which is a translation of the depth of the interaction, basically. It's the same thing. So neutrinos have this kind of effect where it can have an interaction higher up in the atmosphere, so you have big footprints, and as you go lower and lower with the interaction, the footprints get more intense and also smaller. Most of the events will be this size or smaller due to the higher probability of interaction closer to the ground. So now we go to Auger RD, and I have here a comparison. On the left, I have gamma events. On the right, I have, with the same geometry, some electron-neutrino charge current events. On top, I have an interaction that occurs very high in the atmosphere, and you can see that there is not a big difference. It's slightly smaller, the footprint, because it's slightly closer to the ground, but it's still pretty much the same. But most events will look something like this, which is very, very different from a regular shower, because the interaction occurs closer to the ground, so you have a much, much smaller footprint. So RDSim can also do tau propagation, very simple, in a very simple way. So it's basically the same thing. You have an interaction at what I call here H0 that produces the tau lepton, and it has to be propagated until it decays, if it decays above the ground, otherwise it's completely invisible. And then we inject the products of the decay from tauola and create the shower and the radio emission. Okay, this is done actually outside of RDSim for speed reasons. So it's a very simple toy model based on the probability of decay per unit length. So we propagate the tau after sampling the first interaction of the neutrino, and we propagate it. It's very simple. And from that, we get the fraction of taus that decay above ground. And for those, we parameterize the position of the decay. So inside RDSim, what we have to do is just check if the decay occurs above ground or not. And then if it does, sample this decay height. And this is what we get also at OGRD. Here I have tau decay that occurs very high in the atmosphere, which is very improbable, actually. Very big footprint, and something more sensible that decays closer to the ground. And especially at DRD, this effect of the decay, especially even at mid energies for us, is really very rough on the event count. So we don't expect this. Most of the taus will decay below ground and be invisible. So that's it. The next steps that we want to do is do mountain events. So we are working on a kind of a rock depth map. And after you have the tau exiting the rock, it's basically the